thank you very much for inviting me. I hope this will be an interesting meeting and hopefully get to discuss with people I haven't met before. So I'm happy that I'll actually give an introduction because I get a little bit more to the point. So I'm going to talk on basically some studies we have done with the hydrogen on platinum surface, and it's based on a DFT. But let me see. Okay, I'm Kari Laasonen. I come from University of Aalto University, which is it's a town Espoo, which is just very close to Helsinki. So we are in Finland, north part of Europe, and it's close to Helsinki. So that's the geography. Okay, so we have done. Okay, my background is I've done quite a few things, but my background is from ab initio molecular dynamics. So we've done a lot of molecular dynamic simulations, and of course, at one point we decided that we want to do this to study the hydrogen evolution reaction on platinum as carefully as we can. And Axel Gross and Segong has done very similar studies, so this is quite simple. So, and here we have this, basically we're interested in this Volmer reaction, and in this case Tafel reaction. So Volmer reaction, the point is that we have solvated, oops, there probably should be a, yeah, sorry, here is the solvated, this is the proton in water, so it's bound to the hydronium ion, and then the electron is on the surface, and then this is the starting reaction, and then at the end we have hydrogen on the surface. Very, very simple reaction, but having all the details there is somewhat challenging. And then the Tafel reaction, we have looked at both the Herowski and but now we look at the Tafel reaction, is that where we have two hydrogens on the surface, they recombine and you get the H2. So hydrogens, protons from the solution, from the acidic solution, then electrons from the electrode, and we get hydrogen. Very simple. And this, the platinum is the best, or among the best catalysts known for, at least from the pure metals. If you do some mix dope platinum with some other metals, you get slightly better. But platinum is one of the best catalysts for this reaction. Yep. And this is a bit similar picture than Alex showed. So what we can do, so we have a slab, we do a DFT, as Alex did. We have a slab of platinum atoms, then we have the water, some vacuum, and then we have the and the hydrogen on the surface. So that, and then we do this ab initio molecular dynamics. So it's a DFT-based molecular dynamics, and we run it hopefully long enough. Well, that depends a little bit how generous your computer center is. Luckily, we have fairly generous computer account. So, and then of course always in the computations, it would be nice to have several coverages of hydrogen. We only choose here two coverages, say full coverage and the 3/3. And the very similar system, so 6x6 surface, we try to make the surface as large as we can, but the computational cost limit that one quite a lot. And then there's quite a bit of, in our opinion, enough waters. Technicality, I talk a little bit of this DFT model on the next slide. So we use this RPBE. There are billions, unfortunately there are thousands of, or not thousands, but maybe hundreds of different DFT models. So it's rather annoying to know what to choose. But this is very common, this PBE, RPBE. We use so-called van der Waals corrections, empirical corrections to take better into account the weaker interactions between the molecules. But this is very quite standard approach. The one challenge is that in this kind of ab initio MD, we have done many systems. For example, if you have a sodium chloride surface or any insulating surface, then the simulations are very easy. But here the challenge is that this code CP2K is tuned for the high band gap material. So it converts pretty efficiently if you have a high band gap. Water has a huge band gap, so it converts very well. but the metal has, of course, it's a metal, so there the convergence is a bit slow, and this is a computationally quite slow process to get the metal wave functions to converge every single ab initio MD time step. So our time step is 1 femtosecond, and so we have to do tens of thousands or hundreds of thousands of steps. So that's the is a challenge. We use the constant volume, so the volume of this system does not change. Here it's no problem because there's a vacuum interface, so the water system has its correct pressure. There shouldn't be much strain in the platinum side. So this yeah. And okay, this is published in a couple of years in ACS Catalysis. So there you have quite a lot of the details and also some of the supplementary. So this is the computational setup. But now I have to go a little bit. We've done quite a few studies before having this sort of the kind of final simulation. First, it's interesting also to understand that because now we do molecular dynamics. So of course, it's important to understand what is the structure of the hydrogen. So where the hydrogens physically are. So the top side is basically have a platinum atom. The hydrogen can be on top of it, or the hollow side, it can be in between the atoms. And this is it's rather easy to look at that one in a gas phase, but now we can do this in aqueous phase. So it's in this water, platinum hydrogen water interface, and do dynamically. So we'll see that this is definitely, if we have a coverage of 1, here, this is the coverage 1, so then all the hydrogen atoms are on the top sides. If you have a lower coverage, there is like the 2/3, then you have a distribution, some of them in the top side, some of the hollow sides. So clearly the binding site is coverage dependent. And they are also relatively mobile, especially on these smaller coverages, but even here they move quite a bit. They are not very, even on this relatively short time scale of ab initio MD, they move. There's some exchange processes in the full coverage, and on the lower coverage they can go from hollow side to top side and back. So there's definitely, they are dynamical. And this is the water, so it's interesting if we have 0 coverage, we have certain oxygens or that are very close to this is on the hollow sides, but immediately we add some hydrogen, this peak disappears, so with every coverage, the water goes a little bit higher, further from the platinum surface than it is in the clean surface. But with any interesting coverages, these 2 highest ones, there's no changes on this very short distances. So we get information on the sort of, there's no chemical reactions yet, but at least on the system. Then there's another issue, always, never trust a DFT person. The DFT, I mean, this is getting a little bit difficult now because we do huge amount of DFT calculations, but you should always be a bit aware that the DFT is never super accurate. Of course, if you talk with quantum chemists, they can do their single molecules very accurately. DFT is also accurate, but you have to be a little bit suspicious, and especially because now this is a fairly complicated system. You have a metallic environment, you have the water, and you have the hydrogen. So it's definitely, if you think of like a quantum chemistry point of view, this is a highly non-trivial system. It's not a single atom. It has all kind of. So what we did here, we tried a couple of. There's some. Okay, what we do here. This is the coverage with respect of the voltage, and the voltage. Axel mentioned it slowly. What we can do, we can compute the Fermi energy of the system, and we can compute the vacuum energy, and there we get this voltage, and we subtract this 4.44 volt of that particular number. You can argue a little bit that this is exactly 444 or something else, but we use this 444. So what we have done here, this is the experimental data, and now this is somewhat embarrassingly, there's no water here on this solid line. So we can of course put hydrogens on the surface. We can just look different coverages, and we can compute the potential. So we get this voltage coverage relation. We can compute, and what we are quite happy that this PBE, RPBE, these are the two models quite commonly used. Then there's another third model. So you see that very nicely this the experimental data is in between these two DFT models. We've done it also for 100 and 110 surface. So this is a consistent behavior. So I just saw here the 111 surface. And then if we put the water, these are these dots, so we can put the water and do the same thing. We can get the potential. There, I'll show a bit later, but this is somewhat challenging to get the voltage to converge on this molecular dynamics. So it's quite noisy function. But clearly at zero voltage, or we definitely, or a little bit negative voltage, we get the full coverage. Adding the explicit real water molecules, this goes a little bit off. So this might be that, this agreement, the agreement is nice on the without water, but the water disturb a little bit of the potential. So we have to something like 0.2 volt. That's from electrochemists. That's relatively large difference, because they are talking of. If you do the experiments, they make big noise that this catalyst is better in, say, the hydrogen production is a bit better and voltage differences. They are talking few hundreds of electron volt. So, but okay, but clearly we are not terribly badly off. Now, if we go to try to look this chemical reaction, this is of course what we are interested in. So this static thing, and Axel mentioned this Nurskov thing. This is nice. It will give some idea what might be, how the hydrogen is bound of any catalyst. It's very quick calculation, but now we want to see the reaction barrier. And the method we're using so-called thermodynamical integration. You can get from atomistic simulation the free energies in many ways. It's a bit tricky. It's very easy to get many other quantities, but the free energy from molecular dynamics is always somewhat tricky. You need to get some technique. So we use so-called constraint method. I'll have a few slides. So we can define a constraint on this. We drive the chemical reaction by pushing the atom or the hydrogen away from the surface, and then we can basically put some distance dependent. They are always distance dependent constraints. They can be fairly complex. Whatever constraint we put, then we can this value. We set this zero value. Then we can get the force acting to the constraint, which is very very close to the Lagrange multiplier on this technique. So we can get this force, and then of course we have to integrate it. We start, for example, one hydrogen on the top side on the surface, when we start pulling it up to the liquid, and then we have to do this one in a few steps, like something like 10 steps or so. So this is the technique, and then of course technically everything is moving in this when we fix this with one of the constraints. So we fix this one to certain height or distance. This constraint is fixed. Then we do molecular dynamic simulation. We can collect the data on the constraint force, and we can average that one up on these windows. Then we can get this one of the point, and we can at the end we can integrate. We can get the Helmholtz free energy. Oops, I don't need to go there. Let's see. Here is some comments. It comes from this Michael Sprick and Gicotti paper. This idea that we can use the constraint. The constraint force is very close to the Lagrange multiplier. So Lagrange multiplier, we move the atoms a little bit, then we impose the constraint, and from that we can compute always the Lagrange multiplier for that system. So, and there are some small corrections to that one. We tested another paper. These are something like 0.2, some milli-electron volts. So this is much, much more than our noise or fluctuations. So we are very happy to use this simple relation. Of course, the raw data, because it's relatively, if you do a very short simulation, is quite noisy because there are always, when you're looking at this hydrogen, there are some molecular collisions. Of course, the molecules are moving. They can get quite. They collide each other, so the instantaneous forces are fairly large. And what we did, it seems that the like 10 picosecond simulation per single point is enough. This is also convenient because now we are looking. Because we do, this is the output of this, Volmer reaction. So once we get quite a few points, so we see that for us, it's also, we have done quite some of them. So once they follow nicely some curve, then we know the error bars are fairly small and we don't get very abrupt jumps. So we have, if you have some bad constraints, we have a couple of times seen that this goes up, and then it drops suddenly. So there's, so then there is something going wrong. And we mathematically or chemically we know the constraint. Okay, the real reaction path is multidimensional. So every atoms, or not every, but quite a few atoms are involved how the reaction happens. And now we do this constraint is we have some projections of the, hopefully, the true reaction path. And if this projection is not good, then you get some crazy things. I'm not sure if you know this meta-dynamics at Parinello, but basically you can, if it's not a function, the constraint is not a function of the real reaction coordinate, you may push it up and then it drops suddenly. So this is an indicator that your constraint is not good. Unfortunately, it's not so easy to know that one in advance, of course. But we play these few constraints and so we got it fine. So now we got, and then of course we integrate that, we get quite nice curves. And now we did this. Now I'm sure that on the one full coverage we start the reaction from the top side. Now I don't remember precise. I'm pretty sure that also with the 2/3 coverage we start the reaction from the top side. But sorry, I didn't do the calculation. It was my PhD student. Okay, but yes, the important point that we got these graphs, and basically this is the raw data, so the forces, and then when we integrate, we get quite nice barriers. Then we did another paper. Okay, I mentioned a little bit, but then I a little bit forgot that we have this static calculation also on this paper supplementary. So I don't know if you know what is a NEB. Just Hankelman. So he's one guy here was the developer with the NEB method. I saw his name on the So basically the NEB is there are multiple quantum chemistry algorithms. If you want to go from you have some chemical reaction, and the NEB is it will try to find or it will find the reaction path, and this makes a lot of sense in the like gas phase reaction or classical chemical reactions. There's nothing disturbing it. Now this concept is a bit challenging because it is in the liquid water. The environment is fluctuating constantly. But we started this business of trying to understand the electrochemical things first using this NEB method, and sometimes it works. This is what we can do is that we can take, if we have this is what I call initial state and the final state. So if I start my system, the geometry that is resembling this initial state or the And then I can optimize it, because I have to basically optimize all the waters. I have to have in local minima. Then I can push this is static calculation, and I can do the computations by starting from the initial state, push the initial state means that I take the initial geometry and optimize the structure locally, and then I push my reaction. Of course, I still have to know the final state, but I can get some. But the main problem here is that I get very different barriers, and if I optimize the initial state or the final state, so I get much lower barrier. So here this is not reliable, and it makes sense because you are in a liquid or fluctuating environment. So if you have a gas phase, you have two molecules that just collide, they get to each other, they react or not react, that's it. But now, because the hydrogen is approaching, its environment is fluctuating, and then this, for example, on this Volmer reaction, we get very different results, or completely wrong, or unreliable barrier. So one way you get 0.2, another 0.4. So this is a huge difference. Whereas on this Tafel reaction, which is this hydrogen forming, so you have two hydrogens on the surface, they come together and they form the molecule. This is a much simpler reaction, or it's not really much affected by the liquid environment. So it's mostly surface reaction. So there, with this, I would say this is good. Oops. This is good enough. So you can never ever get barrier super accurate. It's always computationally rather delicate system. So for this Tafel reaction, yes, this kind of static-like approach is fine, but not on the Volmer. Or any reaction where you really have, like if you would like to look at the chlorine ion coming from, or to the, say, really solvated ion coming to the surface. So then, because the environment is fluctuating and changing, so that's why there I think you really need the entropy or the dynamics of the system. And we have another paper with we benchmark these ideas in the simpler system than the metal surface. We look some carbon nanotube with carbon nanotubes. Nitrogen-doped carbon nanotubes are quite good catalyst in electrochemistry, so we spend quite a lot of time looking them in the beginning. They are much easier because even they are sort of metallic, they are not as difficult as the platinum. But here we get basically, we did it here the only one way, but the main point that on this case, if we look this initial type thing, then we get the barriers are quite fine, but the reaction energy. So basically, if you look, this is the reaction energy. You see that here with the constraint DFT or ab initio MD, we get something slightly negative values, whereas these are highly positive. So it's clearly this. And now I saw the previous one. I'm even a bit skeptical of the barriers. So you really need to take into account that the atoms are moving. Then Axel already mentioned it quite a few times. Now there is another somewhat awkward problem with any simulations you are is involved on electron transfer on a very small systems. That the electronic potential, we have done that one for another couple of other systems. So the electronic potential varies a lot. So in reality, you have a huge system, 10 to the power 20 or so atoms. And what the electrochemists say, you do it in a constant potential. So you go to the lab, you look what is your potentiometer tells you with respect of your platinum electrode or whatever reference electrode you prefer to use. And then you can see the current, you can change the voltage and you see what happens. And this voltage basically is constant because you have a huge system. Whereas what happens is that when we have this, our tiny system having, even if it has 1,000 electrons or so, it's still very small. And because the electrostatic is long range, so even the proton comes comes to the surface, it's obvious that the charge will change. That's for sure, because here you get proton. The electron is on the surface and the proton is in the liquid. Here you get the hydrogen on surface. So it's obvious that you get the charge is not constant. The surface charge is not constant, because but then it's the other issue is that the electrode potential will also change. This we could easily compute the electron potential when we have the static calculation. Like I said, just a hydrogen on the surface is trivial. If you have I saw that this is nice thing that with the nib type thing, we have still a static thing, so it's easy to compute here. But here it's whenever you let the atoms to move, the electric field is fluctuating quite a bit. But even the data is not super nice. I'm still very confident that on average we got it quite right. So we got this change of the. So we can measure during these constraint simulations the rough change of the electrode potential. And then, what I saw a bit later, we can then use, this is a model by Cheng and Norskov. They observe this very strong size dependence on this proton coming to the flat, empty surface. So they basically develop this kind of conductor type correction to it. So we can, once we got the charge each point and the voltage each point, we can estimate the so-called, this is a model for this constant, on the real barriers at constant voltage. Based on this paper. Some people has criticized that this is not super accurate, you should do it in other ways, but well, that's one way. And this is nice, this can be done without any sort of extra tricks. You can use very standard ab initio MD codes. You don't need to have any constant potential ab initio MD methods. This we found that also it's convenient. This NEM calculation, that I kind of forgot that we have it on the paper. Because this is a static calculation, there of course we get this voltage very nicely. So this is a good way. Even maybe that the barrier itself is not very reliable. At least we have the certain geometries, and we see that the voltage behavior is pretty similar than it is in the dynamics. And at least the error bars we see in the dynamics is not, hopefully not crucial. Yeah. And then what we can do at the end, we can basically take these corrections with different voltages. We can get, and then you see that of course here the voltage is, say, close to zero or a little bit positive, and then the lower the voltage gets, the lower the barrier gets, and the reaction with getting here is thermoneutral, here is with exothermic, but clearly the barrier goes down. We can put these maximums and we can fit quite nice parabola. So I think we have a pretty good understanding what for example here, that what is the potential here around zero. This is our best estimation of the reaction barrier for this reaction, for the hydrogen, the Volmer and Heruski reactions. Sorry, Volmer and Tafel reactions. And then we can collect, and it's quite interesting. It seems that, okay, the red one here is the low coverage. The blue one is probably the correct coverage. So it's very likely that it's zero and a little bit negative voltage. The system is fully covered. So this is probably the more realistic one, the blue one. But interesting that with lower coverages, it seems that the Heruski reaction is or this hydrogen approaching reaction. This is the rate limiting step at one coverage of 1, but then this Tafel reaction is the rate limiting or the higher barrier at lower. So these two reactions are clearly competing with each other. And these barriers, when we got it first, we thought that they were pretty high, because there's this very important or seminal work of Markovits and all, and they've done this one experimentally in 90s. So, and they claim that, or they say that the barrier is fairly low, something like 0.2 electron volt. But then there's a more recent work by Smiegler is involved, but some Chinese persons. So they read and they have a hopefully very reliable result. But then they claim that when I read the paper, is very convincing, so that the barrier is quite a bit higher. And it may be that these Markovits, it's extremely difficult to make very flat surfaces. So there might be that there are some steps or some other defects in this. So this barrier is fairly high. If we do it with the real multifaceted nanoparticles of platinum, then the barrier is close, it's quite small. So this is the flat surface is less reactive, so it has higher barrier. So at least our values are in agreement with the more recent experiments. And we can then put this with these. Well, this is trivial. Putting these two reactions one after another and look how they behave on the with the voltage. So still the barrier is a bit high. We cannot experiment if we take the latest experiments. We cannot say that our results are wrong. It just sounds a bit high, but that's all we can say. Okay, let's see. Oops. And in conclusions, okay, I have a few points. Yes, we can do this kind of very detailed ab initio MD simulations. The only technical trouble is the metal, so that's very slow. We have done sodium chloride surface that we can done 10 times longer, or this simulation would be much easier with this sodium chloride. Then we haven't done, I would maybe interesting to hear, there are a lot of hype now on the so-called machine learning potentials. They might work. There's a little bit delicate point because this charge effect is very non-local. So the machine learning potentials might be good from the local features, but maybe not the global or this kind of long-range electrostatic detailed issues. But we haven't had any. Well, I would like to do, but I don't have a student. I don't have funding for it. Clearly, the entropy that's needed, and to some extent it's quite obvious because the water is not static. So everything is moving, water flows, everything flows. So you need to take this movement or the entropy into account, especially on the barriers that are where the water molecules or environment is strongly involved. At the end, not a huge surprise. The non-constant potential, that is another issue what you need to take into account if you want to get good agreement or with the experiments. And this is really a problem of small systems. Some criticisms of Chang-Norskov model, but we use it, someone can do it. And this, we don't have any proof that the barrier is too high, somehow. Surely one needs to be a little bit suspicious always with the DFT, and secondly with the model, but well, I don't have any solution. I don't claim that our barrier is too high, it just seemed to be a bit high. Okay, I think that was all. So, thank you.